Good one, Logan.
So do we unload
All right.
this already, or is
Just sit back, relax, and enjoy the ride.
It's clearly being sarcastic.
No.
Are you
Sit back, relax, enjoy the ride, and listen and learn. Okay, so we left off yesterday, we were talking about acceleration. Galileo Galilei, born in 1564, died in 16... Yes, died the same year that Newton was born. I think, or is it the other way around? It's that way. No, just sit back and relax. Wow, that's stretching it. Yes, Kate. Just moments after we've had a lunch break, and I use the washroom. All right, go ahead, man. As I was saying, so Galileo. Okay, now I'm going to take it away because you're not listening. You're clearly distracted. Okay. So yes, Galileo was Italian. He was really a scientist, I would say, besides a physicist, right? He certainly dealt with chemistry. He dealt with astronomy. This guy did a lot. I wonder what he got. Like, he must have been independently wealthy. Because no one just does science. Well, no, some people do that, right? But I mean, back then, I don't know. He must have been independently wealthy. So, anyways, he was the first scientist to clearly understand the concept of acceleration. He found that the acceleration of a ball rolling down an inclined plane and the acceleration of a falling object were both described by the same mathematical rules. He was really interested in things falling, okay? And he wanted to know, like if you had a big object and a small object, and if you dropped them, like what's going on there, right? And Aristotle, 2,000 years before, said, well, the heavier one, if it's 3 times as heavy, it's going to get there 3 times as fast. And hard to believe, but 2,000 years went by and no one ever dropped a heavy thing in a light thing. Like, how do you go 2,000 years and not do that, right? That happens to me like weekly.
Yeah.
You drop stuff, right?
Isn't all of Aristotle's things like business?
Certainly a lot, Connor, yes. Aristotle, with all due respect to him, set us back, I think. We as in mankind. Yeah. And no one ever actually sort of stood up and said, hey, that doesn't make sense, right? Galileo was the first guy to really do that. Okay? So I got a little video here that sort of shows you some of Galileo's stuff. Okay?
Is that an old video?
No, I don't think it's particularly old. All right, so looking at this chart of Galileo's experiment, and you're going to do one of these very similar tomorrow. You will notice here that the ball, and I'm just going to zoom in a little bit here so we can see a little bit better. Okay? So we start here at 0, the time. And then the end of the first interval is 0.5, and then the end of the next interval is at 2 meters, and then the end of the next interval is at 4.5 meters, and the end of the next interval is at 8 meters, and the end of the next interval is at 12.5. And clearly those distances are getting bigger and bigger and bigger. And is there a pattern? Of course, the answer to that is yes. Okay, so what I'd like to do is I'd like you to label these interval 1, 2, 3, 4, and 5. Those are intervals 1, 2, 3, 4, and 5. Okay, and then all of this data down below relates to that. Okay, and then the interval number is on the left-hand side there. Okay, everybody good so far? All right, so now just notice that at the start of the interval, these intervals are all 1, 2, 3, 4, 5 seconds, right? The time at the start of the interval is 0, 1, 2, 3, and 4. That's the start of each one of those intervals. And then the time at the end of the interval is 1, 2, 3, 4, and 5. You'll notice that the time at the end of the first interval is the same as the time at the start of the next interval, right? Makes sense. Right? Like I go from 0 to 1, and then I go from 1 to 2, and then 2 to 3, and so on. Okay. What's the position at the start here? 0. That's this next column. What's the position at the end of the interval? 0.5. That's what this value is right here. And that tells me that it traveled how far? It went from 0 to 0.5, so clearly it must have traveled 0.5 meters. And you will also note that because it's at the end of the interval, it's at 0.5 meters. At the start of the next interval, it's at, what do you know, 0.5 meters. And then it ends up at 2 meters, and of course that's where the next one starts, and so on. Okay? So if I went from 0 to 0.5, my distance traveled is 0.5. If I went from 0.5 to 2, then my distance traveled is 1.5. If I went from 2 to 4.5, my distance traveled is 2.5, and so on. And you'll notice that the distance traveled gets bigger. In fact, it gets bigger by how much each time? By 1. By 1 meter. Okay. Now, how do I find the average velocity during the interval? Well, how far did I go in the first interval? 0.5. How long is the first interval? 1 second. 0.5 divided by 1 is 0.5. How far did I go in the second interval? 1.5. How long did it take? 1 second. Therefore, my average speed is 1.5. How far did I go in my third interval? 2.5 in 1 second. 2.5. The average velocities are clearly doing what? Going up as we go down the column. In fact, they're going up by how much? 1 meter per second each time. Okay, here's the hard part. It's not really that hard. I don't know. Okay, instantaneous velocity at the start. The ball at the start is at rest. It's at 0. That's my instantaneous velocity. It starts at 0. Now, if I started at 0 and I averaged 0.5, how fast do I have to be going at the end of the interval? If I started at 0 and I averaged 0.5, how fast do I have to be going at the end, Connor? Or 1, as most people said. Maybe put the phone back in. Yeah. If Connor got 0 on his first test because he was too busy on his phone.
I got 60 on the first.
Oh. I said it hypothetically. Okay. And then he wrote a second test. And he said to he said to me, Mr. Bennett, what did I get on my second test? And I said, well, I'm not going to tell you what your average is now 50. He would know that he got
40.
You got 0 on the first one.
Oh, 0. I thought you said.
You got an average of 50.
So I got 100.
You got 100. How'd you do that? Because 50 is exactly in between 0 and 100. So, same idea. If I started at 0 meters per second and I averaged 0.5, then I have to end up going 1. Right? This one is the average of those two. It's sort of halfway in the middle. Not halfway in the middle. It is in the middle. Now, if I ended up going 1 meter per second at the end of that interval, then how fast am I going at the start of the next one? The same 1. And if I averaged 1.5, but I started at 1, then I have to be going how fast at the end? 2. Right? 2. I average 1.5. I start at 1. 1.5 is halfway between 1 and 2. If I ended up at 2, then I have to start the next interval at 2. If I average 2.5 and I started at 2, 2.5 is halfway between 2 and 3. The average of 2 and 3 is 2.5. And if I ended up at 3, then I have to start the next interval at 3. If I started the interval at 3 and I average 3.5, then clearly I have to be going 4 at the end. And do you see the pattern? Okay. Now you'll notice that the instantaneous velocities go up by 1 meter per second every second. What's my average acceleration? Remember, A is delta V over delta T. The velocity changed from 0 to 1. That's a change of 1 in 1 second. 1 divided by 1 is 1. And if my velocities went from 1 to 2, that's a change of 1 in 1 second, which is an acceleration of 1. And if I went from 2 to 3, that's a difference of 1, and it happens in 1 second, which means my average acceleration is 1. And in fact, the average acceleration of all the intervals is 1. It's 1, which means that every second the speed speeds up by 1. Now, if the ramp was steeper, what would that number 1 be like? Maybe 2, maybe 3. What would it never be bigger than? It'd never be bigger than 9.8, would it? Because that would be straight up and down. That's good. Does that table make sense to you? I hope so, because you're going to fill in another one just like it tomorrow.
Like a lap?
Like a lap. Very similar, and then it's a lap. Okay? Any questions about any of that? No? Good? Good? Okay, I got a little handout for you. You should have, for those velocities on that handout, you should have, well, let me just write down the times. 0, 2, 5, and 10. And your velocities should be 1, 2, 3.5, and 6, right? Okay. So the acceleration is, how much does the velocity change during that interval? A equals delta V over delta T. The velocity went from 1 to 2. That's a change of 1. How long did it take? 2 seconds. 1 over 2, 0.5. The velocity changed by 1. The time changed by 2. So your acceleration is 0.5 what? Meters per second squared. How much does the velocity change here?
A little bit. 2.5 per second.
Between 2 and 3.5 is a change of 1.5. That took from 2 to 5 seconds, which is a time of 3, which is, what do you know? 0.5. Do the last one. You should have got for the last one the same thing. Right? The velocity goes from 3.5 to 6. That's a change of 2.5. It went from 5 to 10 seconds. That's a time of 5. 0.5. Why should they always be 0.5?
Straight line.
It's a straight line. Remember, the acceleration is the slope of the velocity time graph. This is the velocity time graph. The slope should be the same. It's 0.5. Now, flip the page over. This is the velocity time graph. Here, the velocity is not going up by the same amount each time. Right? It's changing. This is variable acceleration. So your accelerations are going to be a lot different. Good luck. When you get to number 7, the last page here has a little bit of a diagram that will help you figure out number 7. I'll be happy to give you answers for all of this tomorrow. Please have it done.
How much homework I have today?
Get started.